Howdy, this video is on electrochemical reactions and how to balance them. Electrochemical reactions are common. Rust is formed by an electrochemical reaction. Combustion is electrochemical reaction. Electrochemical reactions are important in biology. And so electrochemical reactions are important, and it's important to be able to balance them to make sure you understand how many electrons are being transferred. After watching this video, you should be able to identify what is being reduced, what is being oxidized, the reducing agent and the oxidizing agent. You should be able to determine the number of electrons being transferred during an electrochemical reaction, and you should be able to balance an electrochemical reaction. And so one way of remembering that oxidation is about the loss of electrons and reduction is about the gain of electrons is Leo goes Gur. Lose electrons, oxidation; gain electrons is reduction. Now, the oxidizing agent means that it causes the oxidation, and so oxidizing agents are always reduced. Reducing agent is what causes the reduction, and so the reducing agent is always oxidized. And so we can look at this reaction. We have copper plus silver going to copper ions plus silver metal. Now, whenever you have a change in oxidation state, it means it's an electrochemical reaction. And so in this reaction, copper is going from a 0 oxidation state to a +2. So each copper atom is losing 2 electrons. Silver is going from a +1 oxidation state to a 0. And so each silver ion is gaining an electron.
Copper metal reacts spontaneously with a solution of silver nitrate. A coating of silver metal forms on the copper, while copper 2+ ions, which are blue in water, are released into the solution.
So kind of a cool reaction. And so the copper is losing 2 electrons, it's being oxidized. And so the copper metal is the reducing agent. Each silver ion is getting an electron, and so the silver ions are being reduced. And so the silver ions are the oxidizing agent. Electrons are transferred from an atom or ion that is oxidized to an atom or ion that is reduced. And so in the above example, electrons are transferred from the copper metal to the silver ions. Please remember, electrochemical reactions are just about the transfer of electrons. Now, in our oxidation half reaction, we have copper going to copper +2 electrons, so we have 2 electrons. In the reduction half reaction, we have 2 electrons plus 2 silver ions going to 2 silver metal atoms. And so we have 2 electrons in the oxidation half reaction, 2 electrons in the reduction half reaction. The number of electrons in the oxidation half reaction equals the number of electrons in the reduction half reaction equals the number of electrons being transferred. We can look at another reaction. So here we have zinc plus lead nitrate solution going to lead plus zinc ions. And so the zinc is being oxidized. It's going from a 0 oxidation state to a +2. The lead is going from a +2 to a 0. And so the zinc is transferring electrons to the lead. Here we have zinc plus silver nitrate going to silver metal plus zinc ions. And so again, the zinc is going from a 0 to a +2. And so each zinc is losing 2 electrons. The silver ions are going from +1 to the silver metal, which is 0 oxidation state. So each silver ion is gaining 1 electron. And so we have 2 electrons oxidation half reaction, 2 electrons reduction half reaction, and that's 2 electrons being transferred. And so what is being oxidized, what is being reduced? And so looking at this reaction looks kind of complex. And so when you're asked this type of question, the first thing you have to do is figure out the oxidation states of each of the atoms. And again, remember, Leo goes Gur, lose electrons oxidation, gaining electrons reduction. So for oxidation, we see nickel's going from a 0 to a +2. So each nickel atom is losing 2 electrons. It's being oxidized. Now the chromium, that's going to be a +6 going to a +3. And so each chromium atom's gaining 3 electrons. And so it's being reduced. If we look at the rest of the elements, so here hydrogen is a +1, oxygen is -2. Hydrogen on this side is +1, oxygen's also -2. Now, in terms of how many electrons are being transferred, in our oxidation step, we had a transfer of 2 electrons per nickel. We have 3 nickels, so 2 times 3 gives us 6 electrons in the oxidation half reaction. In the reduction half reaction, we have chromium going from +6 to +3, so that's 3 electrons. We have 2 chromiums, and so that's 6 electrons. So the number of electrons in the oxidation half reaction equals the number of electrons in the reduction half reaction equals the number of electrons being transferred. So we can look at a different reaction. So here we have the combustion magnesium metal in oxygen gas to form magnesium oxide. And so magnesium is oxidation state of 0. Oxygen's oxidation state of 0 as a reactant. And then in the products, magnesium is going to be a +2 and oxygen is going to be a -2. And so the magnesium is being oxidized. It's losing electrons. Each magnesium is losing 2 electrons. And so it's being oxidized. That means the magnesium metal is the reducing agent. It's a little confusing. Remember, reducing agents, what's caused the reduction, so reducing agents are oxidized. And so the oxygen is being reduced. Each oxygen is gaining 2 electrons, and so it's the oxidizing agent. And so in the oxidation step, we have going from 0 to a +2, we got 2 of those, so 2 times 2 is 4. So in the reduction step, we have each oxygen is gaining 2 electrons. You have 2 oxygens, so 2 times 2 is 4. So number of electrons in the oxidation half reactions, 4. Number of electrons in reduction half reactions, 4. And so the number of electrons being transferred is 4.
Magnesium has an atomic number of 12 and is a strong but low-density metal. Magnesium metal is highly reactive. When ignited, magnesium metal burns in air to form a mixture of magnesium oxide and magnesium nitride. The light emitted is of blinding intensity. We used a camera with charged coupling devices, or chips, instead of tubes, to obtain these images. The light would have burned an ordinary pickup tube and could easily damage a human eye.
So it's kind of cool. We're going from a springy metal and a gas to a magnesium oxide ceramic.
The oxide is a brittle white solid, in contrast to the springy magnesium metal.
And so we can ask ourselves, will magnesium burn in carbon dioxide? Now, you've probably been told at one point that you need oxygen for combustion, but if you think about combustion as just a redox reaction, you don't actually need oxygen for a combustion reaction. And so we have combustion of magnesium in CO2. Now, if we looked at it, the magnesium is going to go magnesium ions. The CO2 is going to the oxide ion, O2-, and carbon. And then the magnesium plus the oxide ion goes to magnesium oxide. And so magnesium actually does burn in CO2.
Magnesium is placed in a cavity in a block of dry ice. The magnesium is ignited. And covered with another block of dry ice.
And so dry ice is just solid CO2. And so initially all the oxygen is going to be consumed.
Despite the absence of air, the magnesium continues to glow due to its reaction with carbon dioxide. Because of this reaction, carbon dioxide cannot be used to extinguish magnesium fires.
And so hopefully you're aware that fire extinguishers, there's different types, and they can only be used for certain things. You cannot use a carbon dioxide fire extinguisher for a magnesium fire. And so again, combustion is just a redox reaction.
The reaction products are white magnesium oxide and black carbon.
So we can look at different reaction. Is this a redox reaction? Remember, it's a redox reaction as long as there's a change in oxidation state. And so aluminum is going from a 0 to a +3. And so this must be a redox reaction. The iron is going from a +3 to a 0. Now, if we look at what's being oxidized, aluminum is going from a 0 to a +3, so it's losing electrons. So that means aluminum is being oxidized, which means it's the reducing agent. The iron is going from a +3 to a 0, so each iron is gaining 3 electrons, and so the iron is being reduced. We got 3 electrons in reduction half reaction to iron. 2 times 3 is 6. We got aluminum losing 3 electrons to aluminum, and so again 2 times 3 is 6. 6 electrons in the oxidation half reaction, 6 electrons in reduction half reaction, means we have 6 electrons being transferred.
Chemical reactions are exothermic, but none quite like the thermite reaction. Here we have a piece of filter paper which we're going to fold into a cone. We're going to place a mixture of aluminum and iron oxide into the cone. We're also going to add some thermite starting mixture. This is a powdered material which helps the oxidation reaction. We're going to place that then in a hole in this container of sand. I'm then going to place a piece of magnesium ribbon down into the mixture and move the explosion shield into place before we light the magnesium fuse. Now we can take a look at the molten metal by carefully lifting it out of the sand. This white-hot iron is encased in a crucible of glass that has been made by melting the sand. You can see some of the liquid metal as it dripped out of the glass. We're going to allow that to cool down, and then we'll chip some of the ceramic off the metal and take a look at it. Let's now use a hammer to crack off some of that ceramic. Here we see some of the crude ceramic that enclosed the metal. And here we see the metal, the pure iron that forms.
So it's a kind of cool reaction. It's fairly famous. It's called the thermite reaction. It's actually been used in munitions. Some people have speculated that one reason that the Hindenburg went up so fast was that it had aluminum trusses and iron oxide coating on the skin. And so the thermite reaction was part of the reason why the Hindenburg burned so quickly. So we have another reaction here. Is a redox reaction. Again, redox just means electrochemical. And so if there's a change in oxidation state, it means it has to be a redox reaction. And so if we look at the oxidation states, the copper by itself is 0, oxygen by itself is 0. Oxygen is often a -2, and so that means the copper would be a +1. And so the oxygen is going from a 0 to a -2, copper is going from a 0 to a +1, and so this is a redox reaction. And so electrons are being transferred from the copper to the oxygen. Now the copper is losing electrons, and so it's being oxidized. Remember, what's being oxidized is the reducing agent, so the copper metal is the reducing agent. Now the oxygen is gaining electrons, so it's being reduced, and the oxygen gas is the oxidizing agent. And so we saw that each oxygen is gaining 2 electrons. We got 2 oxygen, and so 2 times 2 is 4. Each copper is losing 1. We have 4 coppers. 4 times 1 is 4. And so the number of electrons in the oxidation half reaction equals number of electrons in reduction half reaction equals the number of electrons being transferred. And so it's a kind of cool reaction. Copper just is going to the copper oxide. And it's kind of cool. If we think about it, we can actually go from the copper oxide back to the copper metal if we use hydrogen. And so oxygen in this reaction reduced, it's gaining electrons. Hydrogen is a good reducing agent, and so it can actually cause the copper oxide to go back to the copper metal.
A piece of copper is supported over a burner and is heated. The copper begins to react more rapidly with oxygen from the air, and a darker color can be seen on the surface of the copper. This is similar to the color that forms on copper cookware when it is used in a kitchen. A few seconds later, the copper has become dark. It has reacted with oxygen in the air. The burner flame is turned out, and an inverted funnel with hydrogen gas blowing out of it is placed over the copper. The hydrogen gas is a reducing agent. It reduces the copper oxide on the surface of the copper and causes pure copper to be formed again. The dark color disappears, leaving a pure copper color. Oxidation and reduction of the copper can be repeated several times by removing and replacing the funnel until the metal cools and the reactions slow down.
And so the oxygen gas is the oxidizing agent, and the hydrogen gas is a reducing agent. So if we look at this reaction, we have iron plus oxygen plus water going to iron ions plus hydroxide. And so the formation of rust is just the oxidation of the metal.
When metallic iron is exposed to water and oxygen, it undergoes a product-favored redox reaction. The oxidation of iron produces Fe2+ ion and releases electrons. The iron itself conducts these free electrons to the site of the reduction, where the availability of electrons allows gaseous oxygen to react with liquid water to produce hydroxide ion. Upon further contact with gaseous oxygen, the ions of iron and hydroxide react to produce iron hydroxide, which is visible as rust.
And so if we want to balance a redox reaction, there's a series of 5 steps that we have to go through. The first one is we have to separate into oxidation reduction half reactions. And so what we should do is we should write down the oxidation states for all the elements. And then we notice that the iron is being oxidized and the oxygen is being reduced. And so that gives us our 2 half reactions. Now, the second step is where we want to mass balance each of these. So we got 1 iron and 1 iron. So the oxidation half reactions mass balanced. We got 2 oxygen. And so we only got 1 oxygen on this side. Now, we also get the hydrogen. And so if you're in an acidic solution, you can add water and hydrogen ion to either side. If you're in a basic solution, you can add water and hydroxide ion to either side. And so this is hydroxide, so we're in a basic solution. Now if we put a 2 here, that means we're going to have 2 hydrogen. And so we still won't be balanced. And so we're going to have to add some water here. And so if we added 2 waters and then put a 4 there, I think everything would balance. So we have 2 oxygen, 4 oxygen total on the left-hand side, 4 hydrogen. And on the right-hand side, we got 4 oxygen, 4 hydrogen. And so the first step was to separate into half reactions. The second step was to mass balance each half reaction. Now the third step is to charge balance each half reaction. And so you can charge balance by just adding electrons. And the goal is not to get everything charged 0, but just make sure the products reactants have the same charge, same net charge. And so here we have a 0 net charge. Here we have a +2. And so if we add 2 electrons here, then we'll have the same charge for the products and reactants. Now here we have a -4 charge, and so we have to add 4 electrons to the reactants. And so for this oxidation half reaction, the products are charged neutral, reactants charged neutral. For reduction half reaction, we have a -4 and a -4. Now we got to make sure, the next step, we got to make sure that we have the same number of electrons in the oxidation half reaction and the reduction half reaction. Remember, for redox reactions, you have just a transfer of electrons from one thing to another thing. And so the oxidation half reaction, reduction half reaction has to have the same number of electrons. And so if we multiply this top reaction times 2, then we'll have 4 electrons. And so this is a new oxidation half reaction. We have 4 electrons. Now the fifth step is we just add these 2 half reactions. And again, you can only add half reactions if you have the same number of electrons. And so the electrons cancel, and so this is our final balanced reaction. And so all redox reactions can be separated into oxidation and reduction half reactions. Remember, you always have to add the same number of electrons in the oxidation half reaction and the reduction half reaction. And so there's 5 steps. First, you separate it into half reactions. You mass balance each half reaction. Charge balance each half reaction. Multiply each half reaction by a factor so that you have the same number of electrons. And the fifth and final step is you add the half reactions to give the overall equation. I hope that was helpful.